In this lecture, we'll be exploring the derivatives of trigonometric functions. In this lecture in particular, we will focus on the primary two trig functions of sine and cosine. So we have a very simple relationship between sine and cosine for the derivatives. Specifically, sine and cosine are differentiable for all x in R, and you can see that illustrated graphically. If you think about something like sine of x, we know that sine of x is this periodic function that has no issues with cusps or vertical asymptotes or corners. It's smooth everywhere for all x. Cosine has the same kind of property, and they're both differentiable for all x. And we have this simple relationship that the derivative with respect to x of sine of x is cosine of x, and the derivative with respect to x of cosine of x is minus sine of x. And we want to see why that is for at least one of these, and so we'll actually do the proof for the case of the derivative of sine of x. So remember, as is the case any time you're working with derivatives, we're taking, so why don't we, to be careful here, let's say that our f of x is sine of x and we're calculating its derivative. So by definition, this is the limit as h goes to 0 of f of x plus h minus f of x all over h. So remember, it's important to remember all these different rules for differentiation that we're learning, derivatives of different functions, they all boil down to this same definition. And let's just recall, this difference quotient can be interpreted as the average rate of change over the interval x to x plus h. And when we let h go to 0, that average rate of change becomes an instantaneous rate of change. We can also interpret it as this is the slope of the secant line over the interval x to x plus h. When we let h go to 0, the width of the interval x to x plus h dropped to 0. The secant line becomes the tangent line. So we always want to remember that with these different differentiation rules that we're using, we're always using the same concept that we initially introduced for rates of change and tangent lines. Okay, that being said, our f of x in this case is sine of x. So we have sine of x plus h minus sine of x all over h. And we now start with a trig identity. And we can rewrite sine of x plus h as sine of x times cosine of h plus sine of h times cosine of x. Then we still have the minus sine of x all over h. And we now group things. And so what we will group together will be the terms that have a sine of x. So we want to group together the sine of x terms. So we will have the limit as h goes to 0 of, so the terms that have sine of x we have a cosine of h term, and then just sine of x times minus 1. And we still have this h in the denominator. So this is one term. And then the other term is this sine of h times cosine of x over h. And let's carry this over to our next page. So we have the limit as h goes to 0 of sine of x times cosine of h minus 1 over h plus cosine of x times sine of h over h. So this is just copying that line over to this new page. Now, because the limits of each of these terms will exist, we can use the limit laws to break this limit of the sum into the sum of the limits. So this will be the limit as h approaches 0 of sine of x times the quantity cosine of h minus 1 over h plus the limit as h goes to 0 of cosine of x times sine of h over h. So that again is using our multiplication law for limits. And again, it works because each of these limits will exist on their own. Now, we note that this limit in this first term, and I note I did miss a term here, this should have been a sine of x. This sine of x term does not involve h at all, the limiting variable, which means as far as the limit with respect to h goes, it can be factored out. The same can be said of this cosine of x. There's no h term, so we can factor that out of the limit. So this becomes the limit as h goes to 0 of cosine of h minus 1 over h, and we have the sine of x outside. For the second term, we have cosine of x times the limit as h goes to 0 of sine of h over h. This term, this limit is a quick one. We actually had this as a theorem earlier in the course that this limit is equal to 1. So this term will be 1, and this entire second term in the sum will just reduce to cosine of x. The first term takes a bit more work, and the work comes in the way of using the conjugate. So we've seen this earlier in the course as well, but we have cosine of h minus 1 over h, and to conjugate, we multiply top and bottom by cosine of h plus 1, cosine of h plus 1. Our second term here is just plus cosine of x times that 1 that we just calculated. And we can now concentrate on evaluating this limit. And we know the answer is going to come out to cosine of x, so we hope this limit turns out to be 0. And it will, in fact, do so. And again, don't forget, this is a sine of x. Okay. We have sine of x times the limit as h goes to 0. Let's FOIL this out so that kind of the whole point of doing this conjugation, we get, for the first term, we get cosine of h squared For the outer term, we get cosine of h. For the inner term, we get minus cosine of h. So those cancel, and then we get a minus 1 times 1, or minus 1. And in the denominator, we still have the h and the quantity cosine of h plus 1. Well, we can now start using our limit laws. And maybe before that, we should note that, again, point of this conjugation is that we know cosine squared h plus sine squared h equals 1. If we subtract 1 from both sides, we have cosine squared h minus 1. And then we have to subtract the sine squared h is negative sine squared h. So this means that our expression becomes sine of x times the limit as h goes to 0 of negative sine squared h over h times the quantity cosine of h plus 1 plus cosine of x. And now we merely need rearrange things. We want to start pairing things correctly. We know that we want to pair one of these sine terms with the h and then use this identity here. So we rewrite this as sine of x times the limit as h goes to 0 of, we'll have minus sine of h over h. We still have another sine of h. And then we have our 1 over cosine of h plus 1 term, plus cosine of x. And we can use our limit laws to argue that the limit of this product is the product of the limits. We know that sine of h over h goes to 1 as h goes to 0. So with the negative sign here, this expression will go to minus 1. Sine of h as h goes to 0, that approaches 0. And because as h goes to 0, cosine of h goes to 1, this approaches a half. So this is sine of x times minus 1 times 0 times a half plus cosine of x. But of course, this 0 annihilates that term, and so we just have 0 plus cosine of x, which is what we wanted to show. So this proves that the derivative with respect to x of sine of x is in fact equal to cosine of x. Now that we have this, let's see some examples. So we want to see some of this in action. First example, derivative with respect to x of x cubed sine of x. So what we need is product rule. So the first, x cubed, times the derivative of the second. Well, we just saw that the derivative of sine of x was cosine of x, plus the second, sine of x, times the derivative of the first, which we get with power rule, 3x squared. So we now see how a trig function like sine of x fits into these problems that we do with the rules for differentiation that we already have established. Another example, let's do a quotient rule example. And so remember that the way the quotient rule works. We have the denominator times the derivative of the numerator. Derivative of 1 is 0. Derivative of cosine, remember, is negative sine of x. Minus the numerator times the derivative of the denominator. Derivative of 1 is 0. Derivative of sine x is cosine x, but we have this minus 1 out front. So we have a minus cosine x all over the denominator squared. If we simplify this a bit, here we're multiplying the minus sine x through, so we get minus sine x times 1, which is minus sine x. A minus sine x times a minus sine x is a plus sine squared x. Foiling out this term, well, we have this minus sign. Then we'll have a 1 times negative cosine of x, which is minus cosine of x. And then a cosine of x times a minus cosine of x, so minus cosine of x squared, all over quantity 1 minus sine of x squared. Let's see. Simplifying further, it doesn't simplify much. We just have minus sine of x plus sine squared x minus a minus cosine, so plus cosine x, and then minus a minus, or plus cosine squared x, all over our quantity 1 minus sine of x squared. And the one thing that we can simplify is that sine squared x and cosine squared x do add to 1. So this becomes 1 minus sine of x plus cosine of x, all divided by the quantity 1 minus sine of x squared. So this gives us an example where we use quotient rule of expression and a function involving sines and cosines. How about another example? In this case, we would need chain rule. So to get the derivative g prime of t, chain rule says take the derivative of the outer function. In this case, the outer function is cosine. So the derivative of the outer function, derivative of cosine, is negative sine. Leave the inner function alone, times the derivative of the inner function. So we see a fairly simple example here where we're using chain rule. Another tougher chain rule problem would be the following here, and we want dy du. Actually, let's make this a little more interesting. Why don't we say y equals 2 sine squared u and u equals square root of t? We want to find dy dt. Well, recall our chain rule says dy dt is dy du times du dt. And we'll want to calculate each of these and then plug in. So our du dt is the quick one. So root t is just t to the 1/2, and we know from our power rule that's 1/2 t to the negative 1/2, or 1 over 2 root t. And for dy du, it might be helpful to rewrite that expression for y. That's y equals 2 times sine of u squared. Written this way, we know that this sine squared u is just shorthand for 2 times sine of u squared. Written this way, it'll be easier to see how to take the derivative, dy du. So that 2 stays out front. The derivative of the outer function, now, we have the outer function is the square. So we would take 2 out front, leave the inner function alone, and then reduce the power by 1. But then we need to multiply by the derivative of the inside function. Inside function is sine of u, so the derivative of that is cosine of u. Putting these together, we have, using our chain rule formula here, dy dt is the product of these two, or here we have minus 2 times 2, which is, sorry, that's not a minus, that's just a bad equal sign. We have a 2 times 2, or 4, sine of u times cosine of u, and then our du dt is 1 over 2 root t. And remember, with these questions, you want to eliminate the intermediate variable in your final answer. First we notice 4 over 2, that's 2. But then we have u was root t, so we'll make that substitution. Sine of root t times cosine of root t all over root t. So this gives us an example, a more complicated chain rule example. And I like to show this one specifically because when people do the differentiation chain rule technique written this way, people tend to make mistakes. It's good to rewrite things, to rewrite that sine squared, get rid of that shorthand notation and write it for exactly what it means. And the chain rule step will be much easier if you write it that way. So this gives us an idea of what it's like to differentiate the two fundamental trig functions, sine and cosine, and how they fit into the larger scheme of all our differentiation rules. We will then follow this up in the next lecture where we talk about the other trig functions, tangent, cotangent, secant, cosecant, and we will get into those derivatives, the derivatives of those functions, and how that fits in.